Okay. All right. So very good afternoon to everyone. Thank you once again for coming into our session, the Research Edge session. This is our second edition for the fall 2021 semester. So today we have two interesting presentations coming from the College of Pure and Applied Sciences. So today is very much the sciences aspect of research that we're going to be sharing with you. Two different types of research. So I hope all of you who have logged in today will benefit from the session. So let me remind everyone to ensure your microphone is shut. I'm not sure why I'm not able to mute everyone today. So normally I'm able to, but no worries. So please ensure that your mics are all muted. The session is recorded. So if you need to play back the session at the end of the presentation, you can do that. We will give you the link. So no worries about it. Each presenter will be given about 15 to 20 minutes, followed by about 5-10 minutes of question session before we move to the next presentation. So please try to limit to the time, because we want to end it on time by 3 o'clock, so that anyone else who has scheduled for other classes or other meetings, they are able to leave by 3. So without further ado, let me call our first presentation titled Modeling Sea Waves with Stochastic Diffusion Process and Application in Rising Sea Levels. This presentation will be done by Ms. Wenneka Brown, who's a student at the College of Pure and Applied Sciences, together with her advisor, Dr. Moussa Kounta, who's an assistant professor of mathematics in the college. So let me invite Ms. Brown to start her presentation. You can share your screen.
Yes, sir. Okay. Okay, so is everybody seeing my screen?
Yes, we can.
Okay. So good afternoon to all. My name is Wenneka Brown, and I have been working with Dr. Moussa Kounta, and we are modeling sea wave with stochastic diffusion process and application in sea level rise. So as everyone knows, sea waves, amplitude, and periods are random. So for this research, we use the stochastic process to model the sea wave. Moreover, we use a diffusion process defined by the stochastic differential equation to model the amplitude and the period. Our main results were found by an explicit formula of the probability distribution of the first time the sea wave and its period reach certain critical level and the duration it took to reach that level. The involvement of wave energy in electrical power system make this topic an active research area. Our motivation behind our work was estimating the impact of rising sea due to climate change. Introduction. This research presents a methodology to represent ocean wave based on data observation for significant wave height and wave period. This technique is based on stochastic differential equation, allowing a continuous time representation of the random change in the parameters associated with wave power. Our goal is to find the probability of the first time the wave reached certain height, critical values, and the duration it takes. Why we need to analyze the wave. Rising sea due to climate change. Rising sea levels are expected to cause coastal erosion due to climate change, according to NASA. The sea level is expected to increase by 0.3 to 1 meter. Wave energy in electrical power systems. Converting kinetic energy to electricity. Electromagnetic induction. Electromagnetic induction is the process in which a conductor is put in a particular position and magnetic fields keeps varying, or in some instances, the magnetic field is stationary and the conductor is moving. In this photo, you can see a picture of Brazil as they use metal dams to create electrical power. The disc is sitting inside of the water and is moved by the wave movement and later creates electrical power for the people of Brazil. Rising sea. Rising sea, as you can see in this photo, the period and the amplitude of the wave is not normal, it's basically random. So this is actually our presentation within itself. We would say the house is the critical point. So we are estimating the time that the wave would take to hit this level. This critical level would be the house. Sea level rise projection in the Caribbean. For the Bahamas, we know that we are completely surrounded by water. So this is a projection for the 2050, what we expect to happen as sea level rise. As you can see, the Bahamas is completely emerged and basically it's gone. So we expect by 2050 that there will be no more Bahamas. A diffusion process is a stochastic process xt, where t is greater than 0, which is the solution to the statistic differential equation. dxt equal mu xt dt plus sigma xt dwt, for where t again is greater than 0, where mu, sigma, and xt satisfy the conditions of the existing and unique theorem for SDEs, and WT generates Rayleigh process. WT in this case makes the equation random, and without it, we'll have a basic deterministic equation. Definition 2, the infinity small generator. Let x equals xt, where t is greater than 0, be a diffusion process. The infinity small generator, L of xt, is defined as the limit as t approaches to 0 positive expectation of x xt minus fx over t, where x is a real value. Theorem 2 is a replica of theorem 1, which we'll use for our results. And it's as follows. By Ito formula, again, Ito formula is given by fxt, fx naught, integral 0 to t, mu x, the partial differential equation of x plus a half sigma squared xt, second order differential differential x squared.
You don't need to read the formula. You just can go ahead. Since everybody sees the formula, you don't need to read it, I think.
Okay, that's fine. Okay, so we use the Ito formula, and then we use the Duncan formula. Let f be.
Dinkin.
Yeah, the Dinkin.
The Ito formula will allow us, based on Ito formula, we get the Dinkin formula.
Yes.
And that is our main tool for this research.
Yes, and that is our main tool for this research. So from using the Deakin formula, we get the expectation of where the time hits its critical value. The dynamic of the wave height. Here we see the suicidal wave equation with trigonometric values. And after mathematical work, we will conclude and estimate the parameters.
Oh, after collecting data, after collecting the data, so we don't have, this is h is the height of the wave. The dynamic of the height of the wave is given by this formula, and we see that the orange part is exactly a sinusoidal function. It will give exactly the shape of the wave, and the red part is make it stochastic. So it means that we are not going to have the same amplitude, and every time we have different amplitude and different period in some point. And this parameter is depend to the condition, meteorologic condition. We are going to estimate that, but we don't have real data. So this is theoretical work. So we expect to get a real data and to go further.
Yes. Okay, by simulation of Python, discretization of the height equation was formed. The bottom is a photo of our simulation we use in the Python.
Which
The dynamic of
real data, okay? So we have we just collect random number to give it to the height, but we expect to get real data to get the simulation. And we see here for each different paths. So we simulated for three different paths, and all of them are different. That is make it random. So when you walk by the beach, you see that sometimes when you walk very, very close to the water, sometimes the water will hit you, sometimes it's out. So, and so on, it's going up and down. So that is what we try to simulate here. It's the same in real life.
Yes, sir. Okay. The dynamic of the wave period, similar to the wave height. Again, you can see a sinusoidal wave in the equation as well as the stochastic differential symbol. And like mentioned before, we don't have no real data, so we have estimated the parameters, but as the research continues, we'll hope to get more realistic data. So from the Deacon identity, we've got these probabilistic representation of two classical boundary values where LFX is equal to 0. We find that it yields the probability of H, which is the height at the critical value. And when LF is equal to -1, we found that FX is equal to the expected duration that it'll take to reach that particular height. Okay, so moving along, we have where we've solved the differential equation. LF is equal to 0. And by setting the change in variable, we transform the second order equation to the first order equation. Yes, so we got GHT is the expected equation and C1 depending on the critical boundary conditions. Theorem 4, LF1 is equal to 0, and then we got the probability that it takes to reach a critical boundary point. Similarly, we did the same thing for LF to -1 as we did for LF is equal to 0.
Please go back a bit. What was the last theorem? The last theorem.
This one?
No, previous. Before that. Yeah, so that is what, yeah, explain that one, please.
Explain this one?
Yes.
Yes. LF1x is equal to 0. And from the
LF is an infinitesimal generator.
Yes, LF is an infinitely small generator. So we use the infinitely small generator and we got Fx is equal to the probability of the height reaching its critical value point. And when the infinitely small generator is set to -1, we got that Fx is equal to the expected duration it'll take to reach that particular height.
Yeah, since it's just the since we don't have a lot of probabilities around, so we just say the duration it will take to reach this area, this critical value, the duration.
Yes. Okay, so theorem 5 is we got that G2HT is the expected formula.
You have to get back a little bit next the previous page. So you start with the infinitesimal generator equals equal to -1 is exactly the equation of the duration, and this is a second order stochastic second order deterministic differential equation, and with a variable change, you bring it down in a first order differential equation, and that is the last one we have and we know a formula for that. So that is what you have in the next page, yes?
Yes, sir. Okay. Yes, so for theorem 6, we get that the infinity small generator of height of -1, and we get that it's like expectation of the height at the duration of the height of the critical point.
Yeah, the duration, the period, the duration, the height will get this critical value. Yes.
Yes. All right, so conclusion, as we've mentioned that this research is ongoing. So we are going to collect real data with the help of maximum likelihood estimation. We estimate the parameters.
Yeah, so I think you don't have chance to read the comment, but Dr. Kabir asked which method we are going to use to collect the data. But I'm not I am a mathematician. I'm not a meteorology. So do you have any idea how you are going to collect the data of the height of the wave? Sorry, I'm the first one who will ask question.
Well,
do you have any idea, Brown, that you said that you're going to model to make to determine the height of the wave, but what parameters you need to collect from experimentally that will help you understand or find the height of the wave?
Well, as it stands, I know from a meteorological standpoint, we don't really do oceanography, so there's no way that we could actually get this data unless we open up our research to other countries and probably ask them what they do to determine their expected period and amplitude. But currently in the Bahamas, there's no way that I could say I know of to get this data.
But Mrs. Brown, you're talking to a physicist, so maybe he can have a method.
Yeah, maybe he'll have that method, but I'm talking from a meteorological standpoint.
No, we should minimize our budget. So before we go outside, we should find a way to find somebody who can do it here.
That's true.
All right, at least I could see that you could at least see the not amplitude, we could see the wavelength of the wave, like time to time, seasonal variation. We could see the speed of the wave seasonally, and the wind speed. Probably, I'm not sure, but I can guess at least that those will be the parameters for you to put in your model and then correctly predict the height of the wave. But there could be more. I don't know at this point, but that's what you probably want to explore.
Yeah. Of course, this period, we see that we have a lot of high wave because it's getting cold, and it depends on the season, of course.
Sure.
So, but we haven't explored this parameter, how we get how we get this different parameter, but it will depend. And
yeah.
So when we have this situation, we have what we call, because since I'm working with her and she is a beginner, so in the advanced model, we can find what we call the switching regime. So it means that the drift and the standard deviation, when you collect the data, you try to get the mu is, Mrs. Brown, could you get to the first model, the wave, the height wave?
Okay. That's what?
No, the previous one. The previous one. Go back one. Yeah. So, oh yeah, it's fine. It's fine. Move forward. Okay. So we have here. So the parameter we have alpha, beta, gamma. So we know one period. One. All this. The global one is what we call the drift, and the next one is what we call the standard deviation. Now, the question is the drift and the standard deviation. So it's based on you collect the height, the different height of the wave. So I think it's have a way to collect that in the methodology system. So you collect, and after you plug it to the discrete one. Go to the next page, please. Yeah, so you collect that one. So HT, it will be the wave what you have. This is present, T is present, and it's time today, and T plus one, it will be time tomorrow. Understand?
Yeah, and you see in the chat, Ian Mackenzie really put some idea. You can see that one in the chat, saying that wave heights and periods from the bias in the sea, in the area.
Oh, I see. Thank you, Mr. Mackenzie. Yeah, it's collecting wave height and period from the voice. Yeah. Okay. I learned something new. Yeah, because she told me that she would like to work with the wave. So I found a model quickly, and we start to explore. And I hope we'll able to explore this one further and get a more efficient model.
Yeah.
Thank you,
So
Mr. Mackenzie.
yeah, because at the end of the day, you have a model that can be tested. So now you want to apply it, because remember your main motivation for this study is estimating the impact of the rising sea due to climate change. So so meaning to say you need to have a longitudinal data to actually see, is there an impact, is there a change uh, in the waves, and you have a model now. So I think now what is key is to test it out and use this data for any other decision making on the changes that is happening, which is really impacting countries like in the Bahamas as far as climate change is concerned.
Yes, exactly. So if we can find this data, it will be great. So
Yeah.
we can
Yep.
use this data and compare different models.
Yes.
This is a stochastic model. You may have all the different model and see. And so some people use linear regression, but regression is completely deterministic in some point.
Yeah.
And so it's stochastic, but it's linearity. So the white noise is gone in the calculation. It's a calculation.
Okay, so question from Dr. Curling. Your hands is up.
Yeah, I was thinking, Dr. Kounta, perhaps a random Fourier signal analysis approach could help you get that data as well. You know, getting the PSDs and CSDs of the signal, and getting the root mean square value, and estimating a probability for the height. That could probably help in that situation as well.
Yes.
And another question is, you have a second order equation there, right?
Yes.
And you reduced it to a first order equation to get, well, I should address the question.
Yeah. Could you go move forward? Wenneka to the equation?
Yeah, to the presenter really. Could would an eigenvalue analysis help you there in solving that second order equation?
Because this equation, we don't need eigenvalue. If I use eigenvalue and eigenvector to diagonalize the equation, so it will be very, very complicated. And the question is, what is going to happen here? We will have a matrix, and the coefficient of this matrix we are going to have are not constant, are a variable. And how to diagonalize that one, it will be a big issue. So that is why, yeah, it's better to bring down the order and get it right away, because the first order, we have all the information about the first order. It starts to be complicated when you get second order.
Yeah. So on that note, when you reduce the to the first order, what estimation you made? Like, what was the, how do I say? What did you sacrifice? Like, how much information?
We don't sacrifice anything, because what is going to get sacrificed is DW, the white noise, the stochastic part, and how the stochastic part will get. So because this is the white noise, the expectation of the white noise is equal to 0, and the standard deviation of white noise is equal to 1. And the Ito formula is the main tools of the stochastic differential equation. We use Ito formula is based on Taylor formula, is a Taylor approximation. And when we use Taylor approximation, we stop on 2. That is exactly the Ito formula. And now when the Dinkin formula is working with the expectation, Hello, Wenneka, could you go to the Dinkin formula, please?
Yes, sir.
No, it's yeah, go back. Yeah, it's right here. So the Dinkin formula work with the expectation. So you see that the Ito formula is right away on the top.
I see.
And when you apply the differential echo is a Taylor function, you see that? And when you go to when the expectation intervene, so what is going to happen? The DW will go because the expectation of DW is equal to 0. But of course, we're using a lot of probability theory to convince that is equal to 0. The integral part, the last integral will be equal to 0. That is what we sacrifice.
Okay.
Okay, so thank you so much for the presentation. I think this is an important model, which, as I've said, there's a need, especially for countries in this region, and I hope both of you will take it up to the next level to actually do the test. You got some good comments coming from the discussion today, from the chat today, and I do hope the study will continue. Maybe you need more funding eventually to ensure that this study can be applied. So that's the key part here.
We need really funding.
Yeah. I can see the value of the study here.
Thank you.
So thank you once again, Ms. Brown and Dr. Kounta, for the presentation.
Yes, sir. You're welcome. Thank you for having us.
Okay, so we will move on to our next presentation from Dr. Amin Kabe. His research is a continuation of similar studies that you have done over the few years, and I see a progression on your work, and this is really good because you build on the study that you have done in the past. The deviation of aerosol extinction on various phase functions employed in site scattering LIDAR measurements. So I will hand over to you, Dr. Kabir.
Thank you, Vic, for introducing me. Good afternoon, all. The experiment is about detecting aerosol extinction or the particulate matters concentration in the atmosphere using a technique which we call side scattering LIDAR measurements. So this is a remote sensing technique, ground-based remote sensing technique to detect particulate matters from ground to all the way to the zenith without going there, just from the ground-based instrumentation. And to detect, there is a parameter called phase function that we need to employ. And the phase function varied depending on the day, depending on the location where we do the measurement. And you're gonna show you that how those extinction measurements depend on those phase function. So the experiment, this is a project in collaboration with Central Connecticut State University and NOAA ESRL Global Monitoring Division. The project is supported by the University of the Bahamas Research Fund. So what's aerosols? Those are suspended particulate matters in the atmosphere. They have a size from several microns, from 10⁻³ to 100 microns. And they originate from sea salt, dust, pollen, smoke emissions, soot from biomass burning, volcanic eruptions. Why they're important for a study is they influence the climate change by scattering sunlight and affecting cloud properties, meaning the precipitation patterns, when the rainfall will happen, how the frequency of the rainfall, they are affected by the aerosol concentration in the layers in the atmosphere. And that's why they affect local and regional air quality. To study those concentration, we need to measure a parameter called aerosol extinction. which basically is related to aerosol concentration. Another parameter that we are interested, and the scientists are interested all over the world to find aerosol optical depth, which is basically the integrated aerosol extinction over the entire altitude range in a column of atmosphere. So there are many devices that can detect aerosols in many ways. That could be airborne devices, but the problem with airborne devices are they can find few aerosol profiles for a specific location in the height of the atmosphere. There are radiometers, they can only find aerosol optical depth, but we cannot really get how much is aerosols in different layer in the atmosphere. And then, of course, there is a very versatile tool, which is traditional LiDAR, a remote sensing laser radar, which can profile aerosols, but they are very expensive, more than $100,000, which we cannot afford. So what we have utilized is called a CCD camera-based imaging LiDAR setup. We call it CLiDAR. And this is given by by John Burns from NOAA, with whom I am now collaborating our research. And this is also called CCD Labs, which is given by Chinese university professor in Peking University. So in this setup, in this remote sensing setup, we use a LiDAR, which is a green, we use a laser, which is a green laser and transmitted vertically into the atmosphere, which is shown by the green arrow. And then we set a CCD camera with a fisheye lens, which means it can give us the wide angle view. And the camera takes the image of the laser from the ground to all the way to the zenith. So what the camera really takes is the scattering of the laser beam when it is passing through the laser and scattered off by the particulate matters and the molecules in the atmosphere. So that scattering is collected by the CCD camera. So the use of wide angle lens is beneficial in this case because it can really collect everything from ground to all the way to the zenith without really changing the orientation of the camera. And one good thing is we do not need to have a timing device. So since there is a pixel field of view, means each pixel can have a range of data, range of Z or altitude. The altitude resolution gets better with decreasing altitude, meaning that at the lower level, we can really differentiate the aerosol layers. But as the height goes up and up, really high, then the aerosol, the detection resolution gets worse and worse. But we really don't need to go up there too much. If we can detect within 5 kilometers, that is enough to really study the environment and climate change. So what CLiDAR measures is a side scattering of the laser beam, and from which altitude it measures, that can be calculated from the geometry, just simply using the trigonometry that, okay, that scattering is coming from that altitude. In the traditional LiDAR, that scattering height is measured by the timing device, very expensive timing device. And they also need to use a special kind of laser, which is called pulsed laser, which is also expensive than the laser that we use, which is called continuous wave laser. So scattering altitude Z is determined simply by using the geometry without the need for scanning. And we don't need to have any time gating to calculate Z using expensive electronics in this setup. Here are some of the pictures over the years that I have worked with my previous students. In the first picture, this is a setup that we are having on the T block sports field. The second picture shows our collaborators' picture with her students at Central Connecticut State University, and the two pictures actually side by side. They operate their that instrument in a mobile lab, a mobile LiDAR lab. The bottom two pictures on the left corner, these are taken in San Salvador when I visited San Salvador in 2019 November, before the pandemic, with my student Edward Knowles, a very dedicated students. And we did the experiment for 2 nights for 6 to 7 hours, starting from, I think, 6 in the evening and going to 2 o'clock in the next day. Edward was taking, in the other picture, was taking taking data, and mostly he has taken data, most of the data I just instructed, and he did an excellent job taking a lot of data. So he has taken, maybe each day, he has taken more than 100 images. And the camera setup in that San Salvador, and that is done in, the setup was in the GIRES Research Center. So this is the location of San Salvador in a bigger picture. And then it shows the GIRES Research Center, which is at the northern part of the San Salvador Island. The experimental site has an elevation of 5 meters above sea level. So it's just exactly on the sea level, you can say. And the lower picture is shown the GIRES Research Center, where we have done the measurements. We have also done, as I said, the measurements at the sports field at Nassau at UB. I've shown this bigger picture in one reason, because we have taken some parameter from Puerto Rico and also from Cuba. So there are some setups which is called, which is set up by Aerosol robotic network, or in short, it is called AeroNet. So we have used those data to calculate our aerosol extinction in San Salvador. So just to show where Puerto Rico and Cuba is compared to San Salvador. So this picture is the picture taken in CCD camera by in San Salvador. So this is the picture that we analyze. So this shows the entire laser beam from ground to the top, or to the zenith. The picture was taken in 23rd November 2019, and at a local time, 10 o'clock. As I said, we have taken more than 100 pictures like that in each day on 23rd and 25th November. So in our experiment, we have used a 3-watt continuous wave laser, which is a class 4 dangerous laser at 532 nanometers. And we had to use a filter to block any noise, any other light that we don't want to enter in the CCD camera. The camera to laser distance was kept around 72 meters. And we have used 1/22 for this to take these measurements. And also we have taken 30-second exposure time. At the background, we see a lot of stars. And I'll talk about that one, that we also utilize those stars. And there's a potential to utilize those stars to calculate more parameters in the atmosphere. So this image is used for data analysis, where the signal contains a background. Molecular side scattering means that nitrogen and oxygen that are already in the atmosphere, that scattering from those particles, and also the aerosol side scattering. So which means we have to remove molecular side scattering to know how much side scattering is only coming from aerosols. That will give us the concentration of the aerosol in the atmosphere. So we need to know how much is coming from the molecular scattering. And there are models available, and we can utilize Rayleigh scattering model to know how much scattering is coming from the molecules in the atmosphere, which is basically from oxygen and nitrogen. And that model depends on the scattering angle, and it depends on the molecular density. The molecular density can be found by radiosonde data, and Brown knows that because she works in I think Nassau Airport. So utilizing that radiosonde data, we can find the molecular density, and we can find that radiosonde data from a university website, not our university, it's from Wyoming University. That Nassau data is uploaded there, and we can get that one, find molecular density. And utilizing that molecular density, we can find the molecular model, which is given by this graph. If we look at that graph, we see that there is a smaller change in the 3 order of magnitude in the molecular signal for a range of height, which is good for the camera because it means that we can have a linear response for the camera for that entire range. And linear response is very important because it doesn't show linear response, then we will have error in our calculation. And another best thing is near ground levels, since the resolution, altitude resolution is very high, we can detect any subtle variation of aerosols near ground level, which traditional LiDAR cannot do. But that doesn't mean that traditional LiDAR is not better than us. Of course, they are better, and they're better for higher altitudes, which is of course necessary also to study the climate change. So this side basically discuss that how we have determined the signal intensity. First, what we have done, we had fit beam center with polynomial, find the perpendicular, and interpolate pixels along perpendicular to fill fitting array. So we fit a Gaussian distribution, and to find the signal, the area under the Gaussian will give us the signal intensity. So aerosol's single angle side scattering can be found by plotting the pixel intensity at each altitude, then the signal intensity at a region free of aerosols, which are typically at a height of 3 to 5 kilometers above sea level, was normalized to a model of molecular scattering. Normalization means we need to subtract the molecular model from our total signal so that we can get molecular scattering subtracted and find aerosol single angle scattering. But the thing is, since we are just collecting scattering from one angle, that's not enough because we need to know how much is the scattering in all directions. However, our detector is just in one direction. We cannot set our detector in all 3-dimensional direction. But then how to calculate total scattering? So to calculate total scattering, we need to know the dependence of light scattering on the scattering angles. As it's shown by the diagram, as the light passing through the molecules, not all directions, it scatters at the same magnitude. It scatters in each angle in each amount. So this is what we need to know. And we can know that by a NASA Calliope space LiDAR aerosol phase functions. Those are free, those can be downloaded. And we have utilized the polluted continental phase function, meaning that angle dependent scattering of aerosol scattering. So there are some formula that I don't want to really talk much about, but aerosol total scatter, meaning scattering in all altitude, all angles can be found by this relationship, which relates single scatter with the phase function. After that, we can find aerosol extinction, which is the combination of total scatter plus light absorption by those particles. For that, we need another parameter, which is called single scattering albedo, which can also be found by NASA Calliope Space LiDAR data. So what then we did, we used that polluted continental with more other phase functions. So other phase function mean that we got from Cuba, Camagüey, and La Parguera from Puerto Rico. The reason is in San Salvador, there is no aerosol robotic network. So we had to take help close by data, use those close by data to calculate our aerosol extinction. And we could download from the robotic network those data. So it shows that phase function at different location are different in the first graph. So when we are gonna incorporate those phase function to calculate, to convert our single scatter to total scatter, they will be different. So that are shown on those two graphs, that once those phase functions are used, we got a different amount of aerosol extinction based on the phase function used. We clearly see if we use polluted continental phase function, we are getting more aerosol extinction, showing that aerosol concentrations are higher. It's the same calculation, on the same area, but our calculation varied depending on which phase function that we are using. We can see that when you use Camagüey phase function and La Parguera phase function represented by the blue and orange, they are pretty same. And then when you use just marine aerosol phase function, then it shows a lower concentration of the particulate matters or aerosol in the atmosphere for all altitude. So this graph is actually plotted. In the y-axis, we have the height, altitude, and in the x-axis, we have aerosol extinction in kilometers inverse. Then we have plotted in the next graph that how the aerosol extinctions are varying at a different time. So you can see that the local time 9:39 to 9:42 in the first graph. In the second graph, we have a local time 10:42 to 10:49. So this is the data from November 25. So again, there are a set of phase functions that we have used in our experiment. And we can see that depending on the phase function, the aerosol extinction depends, clearly seen by the second two graphs on the right side. And we also can see the aerosol layers or concentrations are changing over time. So this experiment was done a while ago, which is on February 20, 2020, and also February 19 on 7. So it's like the same year, different year, but same amount, around similar time, we have done those measurements. Interestingly, the whole aerosol profile, if you see on the left-hand side, are very similar from ground to all the way to 2 kilometers. You can see the aerosol structure, the layers are very similar. It kind of tells us that seasonal variation, seasonal type or aerosol thickness probably is remaining same in nassau. Then to know how the aerosol concentrations are changing over time in a continuous measurements, like here in the second graph, which is a contour plot for the measurements from 20 to 21.8 hours. it clearly shows the aerosol layers are developing over the time. So this instrument is excellent because it can continuously monitor how the particulate matters, how the aerosols are changing from ground to all the way to zenith. We can see that between time 20 to 21 hour at night, there are almost no aerosols, or aerosol concentrations are very small, over 1 kilometers. But as it is, as the time was progressing, as getting more and more late at night, we could see that the aerosols are developing after that 21.5. We can see a white spot in the contour plot. This contour plot was plotted within the maximum and minimum limit. The maximum limit was 3 times 10 to the power negative 2 kilometers inverse, and the minimum limit was 5 times 10 to the power negative 5. So any extinction which is more than 3 times 10 to the power negative 2 appears as a white spot. Those white spots are coming basically from the cloud. When clouds started developing, building up in the atmosphere, then we could see those. We could detect those by our instrument. So you can see that the clouds are at a height of 750 meters, and we can also see how much thick was the cloud, how much was the thickness of the clouds. So overall, what we have seen that variation of aerosol extinction depending on the choice of aerosol phase function. We also see the temporal evolution or changing of the aerosol concentration at different layers from ground to all the way to zenith. We have seen that at similar time in a year, the aerosol layers are similar. And also we have seen how far, at what height the aerosol concentration goes really zero. We see that above 1.5 kilometers on those days, aerosol concentration goes really zero. Those are called atmospheric boundary layer. So we could identify what's the atmospheric boundary layer in San Salvador and in Nassau by our instrument. So those are some very important parameters that can be utilized to study in situ environment and climate change. What we have really used is a camera, a CCD camera, which cost $2,000. A wide angle lens is $600. A continuous wave laser ranging from $2,000 to $4,000. Currently, I have 3 lasers thanks to the fund from the University of the Bahamas and interference filter. So in total, and also I bought a laptop, which is funded by university. So within $10,000, I could really pull out a lot of important information for the climate change and the study. Future goal is calculate aerosol optical depth using star photometry. If you look here in this image, there are a lot of stars there. I can really use that brightness of the star, and there is something called star photometry, and we can find how much light is extinct while it is coming all the way to the ground, passing through the atmosphere. So that will give us aerosol optical depth, which is another important parameter for the to model the climate change and to understand the climate change. Then integrate aerosol extinction measured from collider along the altitude to calculate AOD. And then we would like to find a MODIS, which is a satellite-based data, to compare their aerosol optical depth with our aerosol optical depth by using a star photometry and our instrument. We are on the process of also detecting Saharan dust, which passed over Nassau during June. I have taken that measurement. Remember, this is after pandemic. And I have done that measurement, taking special permission from UB police. and staying overnight at UB and took the data for 2 days, 2 nights actually. I stayed over there, which are in progress. And then also we have some interesting instrument which is called particle counter, which can determine the size-dependent particulate matter at Nassau and other islands. So this is all I wanted to share with you. If there is any questions, you're welcome. Thank you for your attention.
Thank you, Dr. Kabir, for once again an excellent work that you've been doing over the years. And I see the value of the work that you're doing. And I really do hope the work that you're doing can be replicated or scaled at the national level, and the findings be used for a lot of decision making in the Bahamas. So again, I would like to open the floor to anyone who has any question to Dr. Kabir.
Yeah, so
Yes.
yes, I have a question. It was going very, very fast. I see that you was using a Gaussian. I don't know if it's a Gaussian model or Gaussian vector.
Oh yeah, just a second. Yeah, I'm gonna go there. All right. So this is just a yeah. You know, because I would like to know how much is the brightness coming in the in that laser. So let's just go, probably it's going to help us that. So this beam is analyzed. You know that it's a special kind of camera, and the brightness of the beam or in the pixel depends on how much is coming in there. But since the beam itself has some thickness, which pixel you're gonna take? To find that intensity of the beam at that altitude and each altitude, we first fit the beam and then take the perpendicular of that beam. You can see this, suppose this is the laser beam, we take the perpendicular of that beam, okay? And then after we take the perpendicular, we interpolate pixels along perpendicular to fill the fitting area. So which means we have used a Gaussian function to fit that fitting area. So we have get that Gaussian which was given at the bottom.
So
that Gaussian, and the area under the Gaussian gives us the pixel intensity at that altitude.
So the Gaussian, when you talk about Gaussian, because the one I see below, it looks like a normal distribution.
Yeah.
A normal distribution. So it looks like the Gaussian, the mu is the mean is 13, and the standard deviation maybe something like 13 minus 9, something like that.
Yeah, I mean, I mean, you're talking about mu and sigma. Is that you're talking about?
Yeah, because when I see the graph here, it looks like a normal distribution. It's a bell-shaped curve.
It's a bell-shaped curve. Yeah, yeah.
Okay.
So,
curve.
So once I feed that, yeah, you know, the curve, then you know that the area under the curve is going to give us the signal intensity actually.
Okay, so this is a probability density function, and,
exactly.
and the area is exactly the probability you're looking for.
Exactly, the area under the curve, that's what we are looking for. And to find the area, we need to know the width and height, which is actually the mu and sigma, right?
Yeah, or you can use a z table.
No, but we don't need, because it's easy now. Just use lab and find mu and height.
Yeah, that's true. No, I don't mean to find the mu and height. You already have the parameter mu and sigma. I say to get the probability of the area under the curve, you can use a z table. That is what I'm talking about.
Oh yeah, yeah, of course, yeah. But really, we don't need, because I'm doing it in MATLAB, and then
yeah, it's more efficient.
Can give you the area under the curve. Okay.
Yeah, that's true. All right, thank you.
Okay. I don't see much question coming from the chat. There's something mentioned there. Are there any sources or citations for the presentation? So all the presentation that is done at Research Edge, the next stage will be actually to write an extended abstract that will be published as a working papers, Research Edge working paper series. So within the working paper series, all the references, sources, citation will actually be captured. So for those of you who needs the citations from all this presentation, you can wait for the extended abstract that will be made available and published eventually in the UB website.
Yeah, I think I'd like to add one more if we have time. I forgot to tell that this presentation actually I have published recently in a International Geoscience and Remote Sensing conference. So it came as a conference proceedings, which was a peer-reviewed conference. And a part of those was also published in a journal.
Yes. So maybe you can provide those links as well. So
Yeah.
for those who want to read further, more details on your work, they can actually read the papers that you have already published. Yeah.
Yeah, I just realized that I should have put the link there. So those basically are all those data right there are already published.
Yeah, so you can email me the papers links, then I can provide and send it out to all the participants.
Okay, thank you. All right.
Yeah. For us, Miss Brown have more stuff to do, and hopefully we're able to finish that one by the end of November.
Okay, all right,
Yeah.
that's great.
Yeah.
So once again, a great presentation from both the presentation today, and we can see the value of both the studies for the country. So this really is the way forward as far as UB is concerned in terms of what we can do for the country. So I think what is key, UB is more of an incubator to do the small studies, but you can see the potential for these to scale at the national level if we can get the right funding, which is the key aspect of doing research. So once again, I would like to thank both the presentation, Ms. Brown and Dr. Kounta, and also Dr. Kabir for always supporting Research Edge. You have done a few presentations with us over the last few years, and I thank you for the work that you're doing. So thank you to all the participants who have been constantly supporting all our Research Edge sessions, and thank you for being here today as well. And we do hope to see you in our next session. So as I've said, we will give you the link for today's presentation. And if there's any further information that both Dr. Kounta and Dr. Kabir wants us to send to the participants, so please do email to us by this weekend, so that by early next week, all this information will be sent out to all the participants. All right then, so thank you, and we will see you again for our November Research Edge. Stay safe and take care. Bye-bye.
Thank you, Vic. Thank you all. Bye-bye.